Hello and welcome to EVM programming course. In today's episode, we're gonna look into gas. So you probably are more or less familiar already what the gas is and what it's for. However, we'll go a bit more into details. So the concept of gas represents the amount of computational effort required to execute specific operations on the state machine. Gas is a critical element of Ethereum network, enabling it to function smoothly by compensating validators for their computational work, preventing abuse, and ensuring efficient allocation of network's computational resources. Gas was created on EVM to disallow from running infinite loops by allocating small amount of monetary value into the system. So gas is expressed in the native currency. For Ethereum, for example, it's Ether. And the amount you pay is determined by gas used and gas cost. So let's say that you have a transaction that used 200,000 gas and gas cost is 10 GUI. That means that it will cost you 2 million GUI to run transaction with a given gas cost. One thing here, you see that the gas is charged with every operation. So let's say that we have the easiest contract and we set our gas limit. You can see here that gas consumed for the current instruction is free, so it's for pushing 1. And our total actually does not start from 0 but 21k, because this is the amount of gas that you are charged with just for sending the transaction. This is the base amount of gas that you have to put just for sending the transaction, and then each of the operations, like as you can see, with each new opcode that we are executing, the gas is added immediately. And remember, this is constant, so no matter how many times you execute the same contract, given that the storage is the same, you will always have the same amount of gas charged, but the gas price may be different. So on one day the gas price may be like 10 GUI, on the other day maybe 100 GUI, and it will really modify how much do you have to pay for given transaction. But now, like, everything's cool, but you can see here that different operations require different amount of gas. And why is that really? Well, it makes sense if you think about it for a little while, because for example, imagine how resource intensive is adding two numbers together, like here. And if we have multiplication, we know that this operation requires more resources to run. The same with add mod. First you have to add two numbers and then perform modulo of those numbers. But yeah, they're more or less similar. SHA-3, which is our Ketchak, takes base of 30, but actually you can see here that has additional dynamic cost. Usually the additional dynamic cost that you have, it depends on the length of the data that you are operating. In case of Ketchak, you are actually paying for memory expansion cost. I already told you about memory expansion cost and showed you some exemplary values, so this is what applies here. For example, reading balance has base cost of 100, but you can see here that we have information whether this address is cold or not. So what does that mean, that address is either cold or warm? So you have this concept in EVM that when you are accessing something from the storage for the first time, you are paying way more than you are doing that for the next read. So for example, if you are reading balance of some external address, the node has to find the information about given address in the storage, read it, and then give it to you. But then it caches it in the memory during the transaction execution, and the next time that you are reading it, this is not cold, this is considered warm. That means that you will pay less for that. The same goes with reading value via sload, for example. The same, for example, you have with external code size. All depends whether the address is cold or warm. So basically you can think about it like, if you're reading anything from address, if it's cold, you are paying 2600 And if not, if it's warm, if it was already read before, you are only paying 100 gas. The same goes for S-load. Like first read from the memory is 2100 and all the next ones only cost you 100. But still, caching the value either in memory or stack is way cheaper than reading it, even if it's cached. And now we have S-store, so the base cost is 100, but there are multiple variables here. So static gas 0, but it all depends if either it's warm, then we are having the base dynamic gas of 100. If not, it's 29. But again, it all also depends if we are setting it to original value or not. So yeah, it's pretty tricky. We can check it here. For example, if we are inputting a value and the current value in storage is 0, and before current transaction is also 0, we are paying 22k. If the value was different, then you can see that we are actually getting a gas refund here. That because we have our value 3 before the transaction and we changed it to 0. But for example, in case that we are setting something to 0, current value in storage and original value is 3, it's non-zero, we are paying 2900, but we are getting the 4800 gas refund. And what really is this gas refund? So at the beginning, the idea was that users of Ethereum and Ethereum virtual machine will be incentivized to clean the state and do not bloat it with new values. That's why cleaning the state gave you a huge gas refund. So actually you can get like 50% of the operation gas value back from the refund. So the main sources of refunds were as storing 0, which effectively cleans the value because 0 is default value in EVM. And the other came from the self-destruct of destructing the smart contract. However, it led to an abuse because after a few years, there appeared the concept of gas tokens. Gas tokens leverage the fact that the gas price was different during different parts of the day. So when the gas prices were really low, it was storing a bunch of rubbish data, just to fill up the storage variables. And then when the gas prices were high, you could just go and self-destruct the contract and you would get the huge refund. And it was actually used mostly, from what I know, by MEV bots and flashbot searchers, which were trying to minimize as much as they can the amount of gas they are paying. And actually using this trick, it allowed them to have like immense amount of refunds on their transactions. It means that their trades were more profitable. And there even was some gas tokens like Chi created by 1inch. But from what I know right now, basically the Chi token is valueless. Like no one is using that because of EIP 3529. So yeah, actually you can see in this EIP the motivation of changing the gas refunds is here. What started happening is like the amount of gas spikes were more severe because some people were dishonest and used these gas tokens to drive price for themselves, and they were actually using the blockchain when the prices were high because for them actually it was not that high, and normal users were heavily impacted by that. So EIP 3529 decided to change the reduction in refunds. So basically it removed completely gas refund from self-destruct, and it reduced gas refunds from S-store. So right now it's basically unprofitable to use those tokens. Next interesting opcode that has dynamic cost is create and create to. Like the base costs you 32k just for creation of the contract, and there is additional code deposit cost and memory expansion cost. Why memory expansion cost? Because when you are creating a smart contract, you have to re-put the bytecode to be deployed to the blockchain in memory. That's why you have the memory expansion cost, and on top of that you have code deposit cost, and of course your init code, which is your constructor, also has some execution cost. You can see here that actually like deposit cost is not that big. I mean, in relation to the code size and in relation to S-store, for example, if you want to store something, you have to pay, you know, up to like 20 something K gas. And here you are only paying 200 times deployed code size. So if you want to store like something really big, after some time, the creation of new contract and reading the contract may be cheaper than actually storing it in storage. And this is actually what S-store 2 and S-store 3 does. Those are not EVM opcodes. However, people wrote smart contracts that leverage the fact that deploying big amount of data is cheaper than storing it. And you can use it this way. Because look, like for example, external code copy only costs you 100 plus memory expansion cost plus address access cost. So again, it may be way cheaper than loading it. And this is what S-store 2 and S-store 3 is actually doing under the hood. But this is actually a weak spot of EVM, because calling new contract means that EVM node has to go to the storage, read the whole contract and keep it in memory for the duration of the transaction, because you may use it. And just look how mispriced reading the code is compared to reading the storage. Like the only thing here is that if you are using smart contract as your storage, well, you cannot modify it. It's immutable, so that's the only downside of using this pattern. Okay, this is all cool, but what really prevents you to, you know, pay insane amount of money and actually, you know, create some transaction that is not able to be executed and maybe, you know, achieve some denial of service on the EVM node? The answer to that is having block gas limit. In case of Ethereum, for example, each block may have only 50 million gas. You cannot go over that. And of course, note that, you know, proposes a new block has to first pre-execute the transactions and see if, you know, all the transactions are filling the block space and are not overflowing. Because the invariant here is that you should not combine multiple transactions in single block, so that one of them may not have the required block space. The different thing is if you are having the single transaction that overflows whole block limit. So for example, in case of Ethereum, that it overflows 15 million. So the transaction will be tried to be executed and will be actually reverted due to the out of gas error. Next, I want to discuss the fee market change. So before the EIP, you can set gas price whatever you wanted, and then it was up to the miner who either include your transaction or not. Of course, miners prefer the transaction that will benefit them most, so they pick the transactions with the highest gas price. But still, you can, you know, put like anything. And EIP 1559 changed that, and now you have the base fee that is burned. So no matter what price you set, there is the base that, you know, that is not accessible by anyone. This is actually taken from the system. This if set as base fee, it doesn't exist after the transaction, you know, it is destroyed. So that's why if there's huge need for Ethereum, actually there is more Ether being burned that is being created from block creation, and Ethereum becomes deflationary then. So that means that its value grows because there are less Ethereum than before. So now after this EIP, you have to pay base fee, and then only on top of that, you are tipping the validator. And one addition to that, like I said, that Ethereum may have like 50 million gas, but actually it's not true. You may have something between 7.5 million to 30 million gas block limit, if I remember correctly. It all depends on how much need there is for Ethereum, basically. So if everyone, you know, is transacting and there is really huge need for computation, the block limit may increase by 2 times. However, the base fee will increase like even more. I don't remember if it's quadratic or not, but I know that this is very severe. So it actually auto-regulates the EVM usage. so that the network is not spammed. If there is like huge need, the base fee grows, and this makes some people to wait with their transaction until the fees go down. And the last topic that I want to focus on today is like 63 to 64 rule. So let's say that this is one smart contract which calls another smart contract which calls another smart contract. So let's say that you are passing 200,000 gas here. Okay, and for the ease of calculation, I will not count the gas used, in the computation in this smart contract. So the max amount of gas that you are able to pass here is this. So this is the max that you can send, and the same goes here. Here, actually, it will be around 193K, and due to this rule. Actually, the maximum call stack that you may have from 1 to 2 to 3, this is call stack, and you may have up to 1,043 calls. But as you may already be aware of, due to this rule, actually you won't have basically any significant gas to do anything with that. And you may think, why is there even, such a rule 63 to 64? When I was searching for the answer for that before, I found this one article that said that this rule is there because some of the earlier EVM implementations had very unoptimized journal, that each time that you switch the call context to new contract, they will really heavy on resources. And without that, there was a possibility of the attack on the EVM, but you are going up to the 1024 call stack to the max, and then you are performing operations. And those operations were really heavy on the EVM nodes and may cause some problems. But this is just an article. I didn't find any authoritative answer to that. Okay, and that's all for now. We will go back to the gas when we will talk about Yul, but more in terms of Ethereum and in terms of why certain gas optimizations are there and what underlying EVM opcodes are there to help us to minimize the gas use. Okay, I hope that you learned something new, and see you in the next one.